All right, welcome everyone to a new episode of the Roscoe's Wetsuit Neuro Podcast. I am your host, Toby Passman. On the show with us today, we have a very special guest, Dr. Lew Lim. Dr. Lim is an engineer with an interest in quantum mechanics, and he holds diplomas in medical neuroscience and business and accountancy. He's a recognized expert in the field of photobiomodulation, and he has a passion for designing unique photobiomodulation devices which improve one's quality of life. And you may know him as the founder and CEO of Vielight. So Dr. Lim, welcome to the show.
Thank you, Toby. Thanks for inviting me.
So I want to hear what was your introduction to light therapy? When did you do you remember when you first heard about it, when you first realized that this could actually be something that you take really seriously in research?
Yeah, this started back in the mid-1990s. I was actually based in California, in the Silicon Valley, doing things that are to do with displays, and LCDs and projectors and stuff like that. And also we had a chance to play around with lasers. And at that time, you got to know that photobiomodulations, started way back in the 60s. It was discovered by accident, but a lot of experiments have been conducted since then. And the Russians and the people in Eastern Europe were the dominant knowledge leaders at the time. But when I came across this, there were discussion in Russian literature, and some of it starting to find its way in the English language. So I experimented with lasers, and the Russians were discussing about injecting light into your blood circulatory system through the vein and get its outcomes. Your blood circulation improves and get better outcomes in terms of overall resilience to diseases and recovery, and better markers for your cardiovascular system, recovery from surgery, and a bunch of good things. But if you understand red lasers, you kind of understand, even at the time, that you can penetrate the membrane of your skin. So there is an opportunity not to need to inject this light into your vein. You can just shine into your skin at appropriate dose or power. It gets inside your system. But if you do it intranasally, you need even less power to achieve that, because the membrane in your nasal cavity, the mucosa, is really, really thin, probably the thinnest among all the membrane in your body. And I tried that, experimented with very low power. I found that you can actually make a change in the property of your blood through microscopy. But I didn't really get going into producing a commercial device until like almost 10 years later, for several reasons. Part of it is I was too busy with other things, and part of it is the solid state technology was actually not advanced enough to produce a consumer level product that's kind of reliable and do what you want. So we, with me and a couple of engineers, we started putting together intranasal devices, although we already found out what it can do 10 years earlier, and then started to release them stealth, actually, pretty much under the radar. And it got traction by word of mouth, and we went on from there. We went on to develop with better understanding. We improved the intranasal devices. We produced devices to help with accelerated healing. And then we understood more about the potential for the brain, and we produced the the first home use devices for the brain. And that actually, a lot of it is attributed to, I guess, my knowledge of neuroscience and brain anatomy, what's possible, as well as the properties of light, properties of laser, and then LEDs. And then we went from there.
So going back to, it sounds like some of the earlier research on photobiomodulation, you're talking about the changes observed by microscopy in the blood when there was light shown. What were some of those changes that were initially seen?
So very often you find that when the body is not functioning at its optimum, there is tendency for aggregation, of the red blood cells. So you look under the microscopy, if you're not well, you find that the red blood cells tend to clump together. Some people call it ruler effect, but it's not strictly ruler. It's kind of you get stacked together like a stack of coins. But generally, you find it's come together. Okay, it is not always reliable because after a heavy meal, or you've eaten a lot of fatty food, stuff like that, or if you're under stress, whatever the reason is, you tend to observe this in the system. But whatever it is, we actually together with the people I was playing around this thing with, we actually conducted a lot of experiments. Like we went to several hundreds, and it's been pretty consistent. You could actually observe it. You can do your count. We never really published it, but this is what we knew. It was almost like a given. Do that. If you're not well, your blood aggregates together. You do this intranasal. You put it under the microscope again, and you can see this separation, and the blood seems to be literally flowing on the slides.
And with some of this research that you're saying, both published and the unpublished research that you guys were doing, like what were some of the most intriguing findings?
I think what we are experimenting right at this moment would be the most intriguing, because we are pushing the envelope of what's possible, particularly with the brain. And now we're not doing just simple microscopy with blood samples anymore. We're using fMRI, we're using EEG, we're acquiring TMS equipment, transcranial magnetic stimulation. Not so much actually stimulation, but to be able to observe changes in certain markers in the brain, the behavior of, say, astrocytes, for example. We're getting more sophisticated. We are doing real-time experiments and see if, we're about to start actually, say we deliver light in a certain way in a MRI scanner. We want to see what the real-time, response from the brain is going to be like. We've done that with EEG already. A number of neurofeedback practitioners have been experimenting with it. You might have come across this. So I think this is kind of fairly well established now. You're free to use this. Put a there are like electrodes that are connected with almost like rubber tubes, and the wires in between, and you can put the headset over it and then see what happens in real time. This has been experimented with the Brainmaster equipment. Now some people do it for fun, especially you have some certain equipment from Brainmaster where you can show like avatar, 3D imaging. You literally see the brain, how the brain is responding in real time. some people may argue there is artifacts involved. Yeah, you can do it. You can actually have algorithms and clean up artifacts. You can still see real-time response in EEG. We are also pushing it further and see what happens in microstates. Microstates is kind of emerging. People are starting to think that it is, and I know that some neurofeedback researchers are actually doing this too. Some work were published not too long ago. Microstates that were related to ADHD. I think that's published not too long ago. But we can, whatever the condition is, we do see change in microstates. Microstates is where you can, people, the investigators categorize them into 4 main groups, and they're almost like these microstates are almost a representation of how your full brain is responding. And I think there's quite a lot to it. And so we'll see. We're pushing the envelope to see what's possible. But now we're, this is just touching on some of the things we're doing. Some really interesting studies I think we just got going is on the effects on long-term meditation with the new model that we have called a NeuroPro, where you can adjust the pulse frequency. You can adjust the way that 2 locations are talking to each other. You can strengthen the coherency by putting more power into the phase, the phase pulsing, or you can reduce it by creating an anti-phase, between the both sides. So there are a lot of things we're doing, and what we found was very, very interestingly in just random testing with long-term meditators or people who are sensitive. They respond to certain frequency, that is outside. Our established devices are in 10 hertz or 40 hertz, which is alpha or gamma. And these long-term meditators are responding when they do a sweep of different frequencies. Some get into this temporary, like, altered state, or you might even say enlightenment at high frequencies like 200, 400, some even higher. So these are very, very interesting things. We have that going now, and we want to start another study, perhaps in Toronto, where the company is based, to add EEG to see what's happening to the brain in real time with this meditators too. And there's a lot of stuff we're doing. Now the thing is, the more we know, the more we think we can personalize the parameters. Now we're looking forward to, in the future, to incorporate machine learning to, say, databases or raw EEG data that's uploaded into the cloud to a certain archive, and incorporate machine learning so that we can learn more. Even for each set of data that are uploaded for, say, a certain person or a certain group of people, as we learn, as we change the parameters, we see what's happening. And when we introduce machine learning, we try to see whether we can actually improve the delivery of these different parameters. It could be compared against a set of normative database, as neurofeedback practitioners often do in measuring, Z-score changes, or whatever it is open-ended. I'm hoping to expand this community of people who are using this NeuroPro so that people learn from each other and help each other out, and we might be the people that might be the discoverers of what's happening in the brain.
Right.
with light. Yeah.
So you brought up a lot of things there, some that I want to circle back to as far as like the how the pulse rate of the light affects the overall treatment, along with talking about the new NeuroPro system that you guys are coming out with. But before that, I just want to back up a little bit, and can you tell me what are the main mechanisms that we know of when someone is using one of these transcranial systems or one of the intranasal units? What is going on with the light and the brain, and what is actually resulting in all of these positive changes?
Yeah. Now, the fundamental understanding, the fundamental mechanisms actually center around the mitochondria. Virtually every mitochondria is ubiquitous everywhere, and virtually every cell in the body has numerous mitochondria, except the red blood cells. And what it does is there are chromophores that are receptive to red and near-infrared light in the electron transport chain. The mitochondria is known, to be the energy producers in your body. So they produce ATP, which is the energy currency in the cells, and ultimately utilized by the body, and they're all produced through the functions of the electron transport chain. So the chromophores are there now here is the quite well-established understanding of how the mitochondria work in processing light, and particularly red to near-infrared light, because the action spectrum seems to be within this range of wavelengths. So it receives that, and what happens if the cell is not functioning at optimum homeostatic level? There is often accumulation of nitric oxide, and when you deliver red and infrared light, nitric oxide is kind of freed or dissociated from the from the process or from the electron transport chain, get released into the body. Nitric oxide is known to be a vasodilatator, which means that it relaxes your blood vessels and therefore improves circulation. And there are quite a number of properties to nitric oxide, and at the moment, I have a particular interest in its ability to inhibit coronavirus replication. I can go into that because we just completed a clinical trial, and we're putting together.
I saw on your website, yeah.
So I actually, what before I got into this session with you, I've been looking at our data. I'm actually writing the manuscript. So that is one of some of the properties, but it also does. It improves the ATP. It energizes the cells, which is kind of fairly common sense way to look at it. But the other things it does is people forget to look beyond that and see this modification of proteins. So eventually it gets into the process of transcribing proteins, which eventually leads to modification of the DNA. But protein modification happens all the time. And what it leads to is better motility in the cells. You cut down apoptosis, which is cell death. You improve the brain synaptic connection and neuronal connection. It reduces toxicity in the brain. It actually helps to improve your immune system. So there are numerous things that are happening at the same time. And one of the things that of particular interest when you're looking at, say, the COVID-19 is it actually helps reduce inflammation as well, which is the major cause of death in, especially when the Delta variant was around, caused by hyperinflammation. It helps the body to heal and get back into, recover. So there are numerous things that is all stemming out of the action in mitochondria. But you go deeper, there are some scientists in the photobiomodulation community saying that, yeah, it's not really, it's all kind of debatable whether it's really, you're going to really details about what the mechanisms are, but some are arguing that it could be a modification of the water structure in the mitochondrial membrane that's improving viscosity or reducing viscosity and therefore better function in the mitochondria. So, but I think there's enough work to show that when you deliver red and infrared light, you actually, if particularly when a person is not feeling well, you get improvements in the function in the brain. Yeah, you can literally see, as I've said before, you can literally see the changes in EEG. There is also real-time changes in the blood flow measured through fNIRS or through fMRI. fNIRS is using near infrared light to actually measure the changes in the blood flow, blood oxygenation. A lot of stuff that have been done to show that, yeah, it really does do something.
And is the blood flow and brain oxygenation mainly changing just wherever you're actually stimulating with the light, or are there any particular regions of the brain that are particularly sensitive or receptive to the light?
I think generally, whether it's the brain or the body, the cells are more receptive when they're not functioning optimally. And I think when they're like at optimum level, they're in homeostasis, they don't actually respond that much. And this was actually proposed by some of the earlier work done in China. But we do observe this as well. We find that people who are not really, well, they have some trauma in the body, like a wound or, in the brain, traumatic brain injury, they actually respond better. And those who are really completely healthy, I think doing this actually helps to maintain the healthy level in your body or your brain. So it does no harm to do it regularly.
So it sounds like it might be good to maintain, even if you are still healthy and maybe looking for peak performance. But what you're saying, it sounds like there's the greatest impact, the greatest benefit that the light is able to do to kind of restore function to the cells that are not functioning correctly, or the mitochondria are not working correctly. Is that an accurate way of looking at it?
I think that would be a right way in general to look at it.
And something I'm just connecting here, I know like a lot of neurodegenerative conditions involve mitochondrial dysfunction, and that is something that that you guys have studied a lot, and other companies have seen using photobiomodulation have been doing a lot of research. So what have you guys seen in terms of, I saw that there was just a recent Parkinson's disease trial. I'm not sure if that was finished or still ongoing, but what have you guys seen with neurodegenerative conditions like Parkinson's and Alzheimer's?
So the major neurodegenerative disease is Alzheimer's and dementia. And we had done case reports, and we have done small studies. We collaborate with some researchers in other parts of the world that look into this. But when you want to make a claim for something as impactful as this one, we got to be really careful. Small numbers actually can, well, you're just inviting skepticism. Regulators are not going to look at small numbers because the chances of errors are actually pretty big. But it gives us encouragement that this is possible. So we are doing a large clinical trial for Alzheimer's disease that is ongoing right now. It involves recruiting 218 people. So it is it is quite a challenging clinical trial to do because just by the nature of you're dealing with people with dementia. We are looking to actually incorporating more mild to moderate rather than moderate to severe patients because they're actually easier to to actually collect data and do it properly. Well, that's happening right now, but other groups have done it. There was one paper published in October, done by a group in Texas, 60 people. They showed really good results. Just delivering near infrared light to the brain. So that's all very encouraging. A lot of the Parkinson's study is actually done in Australia. Now they've used our devices, the NeuroGamma, to and also in combination with some other devices to affect the microbiome in your gut. Now they combine that, they're getting some interesting results. We are not on our own doing a Parkinson's study because we don't have the capacity to do so many studies. They're quite expensive. They draw a lot of resources out of the company. We're still a small company, but we are doing other things, and particularly for traumatic brain injury. So we have an ongoing study at Boston University. There are people, researchers at University of Utah that have gone on their own to study the effect on concussion from sports and things like that. I think they're in the process of putting the data together and publishing it. But when you talk about neurodegenerative disease, there is this CTE, chronic traumatic encephalopathy, which is a result of multiple concussion. You're hearing more and more of this in football, right? Retired football, professional football players who, after a few decades, they get into a decline and they lose control of their emotions and they forget and stuff like that. We're actually getting really, really interesting anecdotal feedback from athletes. So now the word is going around that they should try this. If you Google, I guess, photobiomodulation, CTE, or football, athletes, retired athletes, and their effect on them, I think you find a few things. Particularly there is being advocated by a professor at the University of Utah, Larry Carr, who is a retired professional football player. So he's recovered from suspected CTE. The CTE is never confirmed until you do an autopsy on the brain. So he recovered, and people followed him. And, they seem to be doing better. But that's an area that we really want to look at. So that's there are quite a number of possibilities.
Absolutely. So now I want to talk about how both the wavelength of light that's used along with the pulse rate, how those two variables impact the light therapy treatment and also specifically different conditions.
Now, the wavelength is important because, as I've said before, the action spectrum for the response in the mitochondria seems to be in red, which is between 600 nanometers. To near infrared, you can say it goes up to maybe 1500 to 2000 nanometers. And we ourselves, we use 810 nanometers, mainly because of work done by other researchers. In theory, the longer the wavelength, the deeper it penetrates. Now, light is part of the electromagnetic spectrum, if you like, which covers everything from gamma rays, which is very high energy, very fast, frequency, right up to radio waves. As you know, radio waves, long wavelength, and they penetrate virtually everything. So therefore, in theory, the longer the wavelength, the more it penetrates. But there are other factors that have to be considered, like radio waves doesn't really affect your brain because that is out of the action spectrum, right? So, and then there is also, um, take the example of the sauna, infrared sauna. You go there, you feel warm. The infrared is causing your body to feel warm. That's because of the absorption by the water molecule. So at the, at the, say, even in near infrared, at a longer wavelength, what you're doing is actually creating action in the water molecule. And that doesn't really necessarily help the cells to process this light energy and do this fantastic thing. So all you do is feel nice, warm, and comfortable. That's not a bad thing, but it's got a different purpose. Now, like I said, some researchers are arguing that the effect could be on the water structure, and that often happens at slightly longer wavelength, like there's some work published at 1064 nanometer wavelength or somewhere around the 1100, which is longer than what we use. Now, there's another theory here is if you really accept what the hypotheses are, is whether you want to affect the electron transport chain or you want to affect the water structure. Maybe both work. And there's some work already done showing that in around 810 to 839 nanometers, this is a window where there's least absorption by water, so you can penetrate deeper into your body. Excuse me. So water means water in your body, water in the blood. So the theory is we get a purer response from the electron transport chain in the mitochondria. So that is that. Then frequency, there's very little work done in frequency. Frequency, there's pulse frequency. You can have most of the work in a pulse has been done in continuous wave, which means there's no pulse. They pulse because in the early days is because they want to cool down the laser. If you do continuous laser, it gets really hot. So when you break it to pulse, you can get the power, the depth, and in the meantime reduce, the heating. But new work is coming out is in pulsing. We are probably the first to publish a paper to show that when you pulse at a certain frequency, you can see the changes in the EEG of the brain. So we did our first experiment. We published it in, what was it, 2019. When we pulse 40 hertz gamma into the brain, you see, increased power in alpha, beta, gamma, and reduced power, which is kind of surprising. It was non-intuitive. That you can even lower, some amplitude of certain waveforms like delta and theta.
There was reduced power when there was a gamma frequency. You saw reduced power in delta and theta.
Correct. Yeah.
Okay.
And then we saw a greater connectivity overall. Now we also did work. We haven't published yet, just on alpha, and we see changes as well, but a little bit differently from gamma. It's kind of more focused around the alpha wavelength, and we see some effect in theta. But so we're discovering more. The paper is very slowly being written because everybody's busy. So we hope to get it out. And now, as I said, we have done enough. We've seen enough EEG or QEEG images to show that the brain actually does respond in real time. So there's an effect in view. And I said earlier that for meditators, they can feel the difference. So the frequency matters. Now, the other work we've done is not published. Actually, it's just been submitted for publication. Is we are also looking at the effect on things like the flow of the currents in the living cells. When you deliver, say, near-infrared light in your pulse at 10 Hz, yeah, we see very interesting things. We see both stimulation and inhibition. Inhibition is necessary because you need that to control, the processes in your cells. You don't control that, you get the toxicity from continuous excitation. So stuff like that. In that paper, we're also demonstrating the effect on the microtubules. The microtubules are the structure almost like scaffolding to hold your cells together, but in the neurons, it's believed that they also contribute to, of course, the integrity of the axons, perhaps even the propagation of signaling and stuff like that. We find that we are kind of, what we are discovering is complementing some earlier work which shows that when they deliver high power lasers, they can actually stop pain signaling. And that's because of the effect on the microtubules. It just sort of swell together and just block signaling. But when we do it in our experiment, and this is work done with University of Alberta, co-authors are coming out of Princeton and an Italian university, that we are getting the opposite with low power. Actually, there's more depolymerization, means the microtubules are not clumping together, they are more spread out. And this is perhaps the opposite of what high-powered lasers were doing. We just help with maybe propagating signaling better and stuff like that. So this, this is what we discovered, we're putting out there, and people can put in a hypothesis. We will do our own work anyway, but this is stuff that's happening. And we believe that our next stage of work is going to involve pulse frequency and what the effect is. And I believe we will see interesting things too when you pulse it at different frequencies.
Yeah, I wanted to ask about that and how originally you guys settled on, because I know that the couple devices, the transcranial devices you guys have, or you guys have the alpha one, the gamma one, and then the duo. What was the original thinking behind choosing those two specific frequencies? And then also, I guess, kind of building off what you just said, what would be, or what have other researchers found with pulsing the light at different frequencies, maybe in the slower frequencies, delta and theta, or into the faster beta brainwave frequencies?
Yeah, I think 10 Hertz was kind of, if you want to start with a frequency, I think 10 Hertz would be a good one, because it's alpha. You do nothing. You're not performing a task, and you relax. You do some self-reflection. You get into the alpha state, right? And that state is also correlates with the default mode network. Now, the default mode network is also similar. You go into rest. So that's why it's called a resting state network. I think these two come together, and default, just by its description, is like a template network. And if you want to improve your brain and not be getting your brain to do so many things, obviously you want to rest and just close your eyes and get into default mode, which is also alpha. And when theoretically, when you deliver alpha at the same time, you are kind of, maybe strengthen the state. And when you strengthen the default mode, you probably everything's related in the brain. You're probably strengthening the integrity and functioning of the brain. There are some work done in animal studies, particularly done by Michael Hamblin's group in Harvard several years ago now, at different frequencies to see at what frequency the animal model, when it was simulated with traumatic brain injury, at what frequency they will recover most quickly. I think they had 0, they had like 10 hertz and 100 hertz or something. And I found that the frequency that drew the greatest response or the fastest healing seems to be at 10 hertz. So we kind of, okay, looks like you just deliver red or near-infrared light to the brain, which is normally just continuous, is not as good as 10 hertz. So you might as well do 10 hertz. And in the meantime, you can build on this theoretical base. Now, okay, that's one out of the gate. Now we found that when we start trying to address dementia and Alzheimer's, and I studied some of the earlier works, and interestingly, a lot of work were published in 2016 on what happens when the brain is consolidating memory. It seems to be when the brain is consolidating memory, there is a presence of 40 hertz in the brain or gamma. So, okay, you want to consolidate memory to help with maybe your cognition or memory function. You want to follow this idea and deliver 40 hertz. In the meantime, at the end of 2016, MIT, and we were already building 40 hertz to try to address, dementia and Alzheimer's because of memory. Incidentally, they published in an animal study showing that 40 hertz actually does improve the behavior of mice and animals. And also when they these mice that were bred with Alzheimer's symptoms, and what they were doing is these mice in a cage, they flicker lights at 40 hertz, and found that the behavior was better. But they also measured and saw that the markers for Alzheimer's, like beta amyloid deposits, actually reduced. And reduced in the occipital lobe that processes this, this flickering of 40 hertz into your eyes. So yeah, I thought it was a really good paper, and it kind of confirmed my belief that we got to try and deliver 40 hertz to the brain. So what they also found, they developed a theory that 40 hertz actually activate the good type of microglia. Microglia is a group of brain cells that help to remove the debris in the brain and unwanted deposits and stuff like that. So this group, the B group, actually does not cause inflammation, which is different from the other groups. And that helps strengthen the theory. So we did, okay, if you're going to do a study for Alzheimer's, we actually had good results for 10 hertz already for dementia in this case report, but let's do 40 hertz, so we did another, actually UCSF, Professor Denicha of UCSF published her own work using 40 hertz, the gamma, and she incorporated fMRI and found that, this group of 8 people actually improved in their cognitive measures, and the fMRI over 12 weeks showed improvement in cognitive connectivity in the default mode at 40 hertz. So that's why our Alzheimer's study will be built around delivering 40 hertz near infrared light to the brain. So that's kind of, now we are discovering that, okay, other frequencies are doing other interesting things too. What is it? So let's try with meditators, see, how it's going to pan out, what's going to teach us.
Right.
I think there's a lot of discovery to be done.
Yeah. So
Yeah.
the studies on meditators that you guys are doing or going to do, is that going to involve the 40 hertz device, or is that a different pulse rate?
That's the NeuroPro. The NeuroPro allows you to do a sweep of different frequencies. Now the idea is you do this sweep and a person, a long-term meditator meditating will hit is the particular frequency. I'm pretty sure it's not 40 hertz. It's going to be probably above 200 hertz. And they get into a shift into altered state. So that will be, yeah, and we want to see, yeah, what does it look like? You know, what is there a common frequency, you know, that does this to different meditators? Is it very specific? But our next study is going to incorporate EEG so we can see, okay, what the heck is happening to EEG? Actually, we did an earlier a study that we happen to have among this group a couple of long-term meditators. Yeah, the brain is look very different. We treated them as outliers. You know, it's so far different that we didn't count them into the data. But yeah, our brains are all different. And I think I'm not a long-term meditator by any means. But I see this happening, so there's something special about the brains of long-term meditators, actually.
And that's something I've seen, I think, from Dr. Richie Davidson's work with
Right.
long-term meditators at the University of Wisconsin, where he was showing the increased gamma frequencies that they were able to produce. So it makes sense that there would definitely be something there. And tell me about also just kind of the rationale for the development of this new device, and why it was important to create this new device, and what you think, what sort of conditions you might think may particularly benefit from what this new device is capable of doing, related to the sweep, along with the different things you can do with the connectivity that you mentioned earlier.
This new device is, I would say, it is like a tool that, you know, maybe you call it a key that unlocks the door to new discovery. So we, you know, as a neuroscientist, and we've done enough research and work, we know that we know very little about the brain, and what we know, and even the smartest neuroscientists will probably only understand a small percentage of what the brain is capable of. And yeah, let's see if, you know, as more people get into this community and do their work, they play around with frequencies on, you know, different, maybe on themselves or different patients, they will discover new things. We, you know, I think collectively we are going to, I think the excitement is not so much that we know that this frequency is going to do something to this condition. It's more like, okay, let's put it out there and see what we can discover with even a particular condition. Maybe the response to Alzheimer's is not necessarily 40 hertz. It could be different among different people. There was an unpublished work done actually out of University of Alberta that we work with. They found that the greatest signaling seems to be intraneuronal signaling seems to be 39 hertz. And that's interesting. You know, we never thought about this, but we went on 40 hertz anyway. So that is, yeah, what else can we discover? I don't know, but for the layman who uses this, it gives you more opportunity to try yourself beyond 10 or 40 hertz. Who knows, you know, you learn that maybe a certain time of day you have this certain experience. It could be maybe increase of beta 20 hertz or something. What if you try SMR training, and, you know, SMR is what 12 to 15 hertz. And then the other interesting things that are being experimented with TDCS, transcranial direct current stimulation, which is electrical stimulation, at certain pretty well-known group where they are for stroke recovery is a cross-frequency coupling of maybe 17 to 60 hertz or something, give you the greatest response. And there is work done with TMS that also involves cross-frequency coupling. We can do this actually with the neurogamma. We can do cross-frequency coupling and have it, within a longer pulse, you have faster pulses. So you have two at the same time. So that is all possibilities. You read a paper, I say this guy is getting results using electrical stimulation with cross-frequency coupling. We could try it with photobiomodulation. The NeuroPro allows you to do that. You can do it with selected modules on your brain. It could be somewhere between the left prefrontal and the right parietal area or something. So everything is out there for you to discover.
Right.
And more modules, you can move them around. So
yeah. Seems like there'll be a lot of experimentation and cool discoveries made when this new device comes out, and people
the device is actually out. The device is out already.
Okay.
We haven't done. I guess we are not doing a lot of. Okay, we are spreading the word. We haven't actually done aggressive marketing for it. Maybe we should, but it's out there. It's not. It can be for people who just want to have the most sophisticated brain photobiomodulation device for their own and allows them, opportunities to self-experiment. Or it could be for really knowledgeable, say, neurofeedback practitioners who know how they want to train a brain with precise frequency. If they have a EEG equipment that can show them how the brain is responding, I think they will, give them even more opportunities to. Well, we can help your clients. That they have low power in a certain frequency. Say ADHD could be too much power in theta, not enough in beta or gamma. We can reverse that by strengthening the amplitude for certain frequencies or reducing the amplitude. So
got it.
Yeah.
Awesome. Well, Dr. Lim, it's been a pleasure having you on the show today. If people want to find out more about your work, the research, or more about Vielight, where would you direct them to?
Go to the website. There are, I think, quite a bit of information. If there is also a separate page for NeuroPro. I think we put up quite a bit of research material out there that you can look at. And if you have any questions, just write into info@vielight.com, or I think you can, do messaging, or call the number, toll-free number. Yeah.
Great. Okay. And for those of you who enjoyed the show, go ahead and like and subscribe to our YouTube channel. It's Roscoe's Wetsuit Neuro. We just surpassed 1,000 followers. So thank you for that. Really appreciate all your guys' support. And if you prefer to listen to the audio version of the podcast, you can always do so on Spotify, Apple Podcasts, or any of the other major streaming platforms. So Dr. Lim, again, I wanted to really thank you for coming on the show today to share all your knowledge and expertise.
Sure. Thank you for inviting me.
Absolutely. And then one last thing I've started doing that I sort of use this segment as just a quick kind of trailer or intro to the episode. I kind of have started asking guests the question, why should the listeners tune into the show today? So it could kind of be based on, what some of the stuff we talked about, just why it's important for people to know about light and all of this really cool research. So yeah, if there's anything that comes to your mind, like a 30-ish second sort of just response to why the listeners should tune into the show today.
Yeah, what I've just covered can be maybe a little bit deep. There's quite a bit of molecular biology involved and physics, but I think maybe the message, although people may not capture everything, the message that I'm putting out there is photobiomodulation actually does something. It seems is supported by research. Is supported by research, not just cellular research, but also in clinical trials. And the one thing I didn't cover, hardly cover, is our work on, say, the COVID-19 infection. And I'm putting together the manuscript right now. We've got the data, we're putting stuff. I would say that it looks really interesting, and it shows in a way the power or the possibilities with light, using light to help the body. So it doesn't need to be a drug. It can, it doesn't need, there are many ways maybe of doing it, but this is showing the light's ability to do several things. Viral inhibition, healing of the body when it's kind of damaged or lesion, and say reduce inflammation. These are like the three cornerstones of addressing COVID-19. But this is just on the body. We're talking about the brain. That's all. Yeah, it is. When you get to do the fundamental mechanisms, right down to the cells, the mitochondria, which is ubiquitous. These are all the upper level mechanisms that are happening that can help the body and the brain. So that is kind of, hopefully, I'm not overcomplicated things here.
Great. Perfect. No, I think that's perfect. And then one last thing, I can just get like a screenshot I'll just use to kind of promote the episode. So you can just smile here. Perfect. All right. Well, I'll send you the links when I put the episode out. Feel free to share with whomever. And yeah, the last question I always ask people, I know you mentioned a few different researchers. Is there anyone specifically that you think would be interested in coming on my show to discuss their research with photobiomodulation?
There is actually quite a number of, the people who, community who do presentations at a conference. If you go to, I don't want to miss out somebody, but if you go to PBM 2021, I think the conference was late last year, you see a list of names, speakers, and they have topics, titles there that kind of show what areas they're experts in, and many of them would be happy to come in.
Perfect.
Yeah.
Perfect. Yeah, I did find that website. Yeah, the PBM 2021. Okay. Yeah, perfect. Great. Yeah, a lot of these people, some I've heard of, some I haven't. So I'll definitely reach out to some of them. Great. All right. Well, yeah, have a nice rest of your weekend, and thank you again.
Well, thanks for inviting me once again.
Of course.